Okay, well, good morning, everyone. Welcome to X 151 to 51A, Introduction to Digital Design and Integrated Circuits. We're coming to the 12th lecture of the semester, almost halfway of the semester. We discuss the different ways of thinking about transistor behaviors and NMOS and PMOS. We'll talk a little bit more. And in today's lecture, we'll be more focusing on the delay, right? After understanding the transistor level behaviors, and how we actually construct complex gates out of the different transistors. Then the question is that how do we understand the delay, given delay is such an important metric in today's hardware design? Before we talk about the main topic today, I think it has been a lot of exciting news, I guess, in the semiconductor industry in the past couple months, right? I feel like every week there's some interesting announcement with different ways of partnership between different, I guess, companies and different styles of partnership. I guess the news of this week is a new partnership between OpenAI and AMD. So I've definitely seen a lot of movement from those frontier lab in actually better securing different compute capabilities. So I guess the news this week is between OpenAI and AMD. They signed an agreement to actually build 6 gigawatt data center for AI. I have no idea how much power is 6 gigawatts. So I look it up. The entire San Francisco grid is roughly 1 gigawatt of power. So that's the scale that we're talking about from those frontier lab in actually having better access to the compute infrastructure, not only just a silicon, there's like the entire components actually building this kind of very complex AI supercomputers, and this just never stopped, right? So this is a new agreement where they are actually interested in using not only NVIDIA's GPU, but AMD's GPU in actually setting up this large scale data center. So this has been really interesting and exciting. From the hardware side, there's a lot of infrastructure, there's a lot of activities in actually building this kind of hyperscalers specifically for AI. While I was preparing this slide, I feel like there has been a lot of exciting development around OpenAI for the past few months, right? I think we talked about earlier this semester when OpenAI signed a contract with someone to build their dedicated ASIC hardware. Anyone remember who they signed contract to build ASIC? They signed contract with Broadcom to actually develop their custom AI hardware, right? So this is more the AI building side. And I guess a couple of weeks ago, they also have an agreement with Oracle to use actually the infrastructures from Oracle to have better access, I guess, using NVIDIA's GPU. And then NVIDIA and OpenAI also signed an agreement in actually partnership and also better support and the investment between NVIDIA and OpenAI, right? So you look at all the, I guess, different strategic moves from OpenAI, or this is very representative. I don't think OpenAI is the only one thinking about that, right? A lot of this kind of frontier labs are thinking about how to actually have better compute infrastructure to support this AI development. So there is a lot of excitement with actually different partners, especially thinking from lab all the way to semiconductor, I guess, hardware providers in better support this AI endeavor in building this large scale data center. So it's a really exciting time to be in this industry, a lot of different components going on and a lot of different players, right? So it's not only, I guess, they have their custom silicon, they want to have better access to NVIDIA's hardware, but they are also partnering up with AMD to actually use AMD's GPU more efficiently, right? So there are a lot of movement in this space, and it's going to be interesting to see how we better design, better use, and better manage the different flavor of AI hardware. So with that in mind, let's get to the main topic of today. Just a quick recap. Last week, we talked about CMOS transistors, right? We start talking about the CMOS MOSFET behavior, and at very high level, we can think about the MOSFET as a switch model, right? With different voltage applied, we can turn on and off our MOS transistors, and then that will just act as a switch with a resistor here, right? We talk about two type of MOS transistors. One is NMOS, NMOS, which is on when we actually have high voltage. We also talk about PMOS. Gate here, and which is on when we actually apply low voltage here, right? So that's a two different flavor transistor. We talk about 3 terminals, and gate is basically the controlling terminal where input is applied. By taking different input, we can actually have different conducting behaviors between the other 2 terminals. Make sense? Coming back, like all the MOS behaviors, all the different green bubbles, electrons floating around, capacitors, right? And we talk about PMOS and NMOS have different behaviors. In particular, to actually have MOS transistor conducting, what we want to have is the gate to source voltage. Remember, we apply a voltage to the gate, act like a capacitors. It needs to be high enough to actually creating a channel between the drain and the source, right? So it needs to be high enough. And that's the voltage we discussed, threshold voltage, right? You need to go above the threshold voltage. That's when we actually can form a reliable channel and the channels are conducting, right? So that's the gate and the source, so they need to above the threshold voltage. With that in mind, if we actually think about transistor behaviors, we talk about for NMOS, it's really good at conducting zeros, right? Because now we are actually connecting the source to so we want to actually isolate the source and gate voltage, the threshold voltage from output, right? So that we don't get this non-ideal high and lows. And NMOS is really good at discharging to the ground so that we can get a really good zero. We can get really good low voltage, right? Does that come back? With this, we like to put NMOS so that we can have a strong zeros. We can do a discharge. And for PMOS, it's actually good, really good at getting a clean 1. So we have a strong 1 when we actually get output connected using PMOS, right? So that's the PMOS and NMOS behavior that we discussed last week. So with that in mind, we can actually construct different CMOS gate with both PMOS and NMOS. In particular, we start with inverters. So how does an inverter look like? We talk very early on, we talk about inverters, we talk about voltage behaviors, but now looking at understanding the PMOS and NMOS behavior, when we think about inverter, we basically have our input, and then we have a PMOS on the top. We mentioned PMOS is really good at pulling up to get a very strong 1, right? And we have NMOS at the bottom, as NMOS transistors are really good at actually discharging to get a strong 0. So that's why it's called CMOS, right? It's complementary. It has both PMOS on the top to pull up to a strong 1 and have NMOS at the bottom so that we can pull down the charger to get a strong 0. And when we think about the simplest CMOS gate that we can build, right? We have a single PMOS transistor on top, we have single NMOS transistor at the bottom, and by doing this, we can actually invert the signal. Let's say like the input is high, is a VDD, is a high voltage, the PMOS is off, NMOS is on, we can start discharging and the output will be 0, right? So that's the inverting part. And if we actually input is 0, PMOS is on, NMOS is off, and we get a strong 1. So that's an inverter behavior. Now this makes sense. We covered briefly last week like how it's actually inverted by having PMOS on. We have a high voltage, we invert it to a low voltage. But PMOS on, we have a low voltage, we charge it to a high voltage. We have NMOS on, we have a high input, NMOS is on, then we discharge. Does inverter behavior make sense? For high level, how we get to input and output are inverted, right? So in this case, we have actually a complementary CMOS transistor with both PMOS and NMOS. When we think about transistor behaviors, there are always 2 parameters that are important. You may remember, like we talk about, like if we look at top down of MOS transistor, we have gate length, right? We talk about that specific, typically the pitch of the gate, that's the length. And then we have the width of our CMOS device, right? That's like how big the contact area is. So when we talk about transistor, we typically label as those two parameters, the length of the channel, right? How long the channel is. We talk about as we're shrinking the technology, the channel gets narrower, and also the width of the transistor. We'll talk a little bit more later. The width of the transistor has a pretty big impact of the strength, how strong it can drive the later, the following circuit. So those are the parameters that we'll talk about that's related to how the MOS transistor behave. So those are two parameters. So far, so good. Everyone with me? That's like CMOS behavior here. Okay, great. So this is like a representative way of actually building, again, complementary, having both PMOS and CMOS, and this is the simplest gate, right? But this can actually be generalized when we think about more complex gate. Here, we can always have what we call a pull-up network that composed with PMOS transistor, because PMOS is really good pulling up the signal to get a strong high voltage, strong one, right? So we like to have PMOS on top so that whenever we drive the circuit, we can actually get a strong one on top. So we have the pull-up network that pulls the output to high voltage. And then we also have a pull-down network, and those are composed with NMOS. Because NMOS is really good at pulling down the signal, discharge the signal to a perfect zero, right? So we like to keep NMOS at the bottom to pull down the signal to the ground. So when we think about CMOS design style, we always have, again, a pull-up network on top and pull-down network at the bottom that actually get to from input to output, right? So this is like how we think about a CMOS gates, having a range of gates on the top to pull up to a strong signal, to a strong one, and have PMOS transistor at the bottom to pull down to get to a strong zero. So how do those CMOS transistor work, right? How we actually think about the different ways of building CMOS transistor. We'll talk a little bit more, but you can think about the pull-up network. It's basically the dual of the pull-down network, because when you actually pull signal down to zero, you want to make sure when the pull-down network is active, is on, the pull-up network is off, right? So that's not confusing. When we actually like discharge, we're actually discharging to zero. We're actually charging to one. So it's actually the opposite. If we actually have pull-on network on, we're pulling on, the other half of circuit is off. We'll see a couple examples to see how they work, but that's a high level idea of how we actually construct CMOS gates using both PMOS and NMOS. So with that in mind, you will actually notice the CMOS gates are always inverting. What do we mean by that? So when we are using NMOS, let's say we're using NMOS as a bottom, right? Which basically means whenever my input is high, whenever my input is high, my pull-down network is, if my input is high, my pull-down network is on or off. When all my inputs are high, the pull-down network is on, right? So I'm discharging, right? And my output will be low, right? Because whenever my pull-down network is on, I'm actually discharging, right? So if on the other side, and if my input is actually low, it's a low voltage ground, my pull-up network is on, right? My pull-down network is off, right? Means I'm actually charging, so I'm actually get a high output. Does this make sense? Right? How input actually drive the pull-up and pull-down network and get different output. Right? So in this case, that's why we call it actually always inverting, as you get actually high signal from the input, and you will actually get the inverted signal to the output, right? You get high signal, it turns on the NMOS pull-down network, and then I get actually a fully discharged, I get a low voltage. If I have low input, it turns on the pull-up network, I'm actually charging my output, so I'm getting a high output. So if you think about CMOS complex gates, it's always inverting as it's taking a high voltage, a high input, and it always gets a low output. And or the other way around, whenever you have a low output, you get the high input. Does this part make sense? Right? How this part is inverting the input, the output is actually the inverted signal of the input. Right? So now if you actually want to, like when we talk about Boolean algebra, right? We always take, we mentioned earlier, we can always use, I guess, the inverted gates from CMOS is always inverted, and we want to construct the original gate, we can just add the inverter there. So that's why the CMOS gate is always inverted. Make sense? Questions? Mm-hmm.
So the pull-up and pull-down network is different on polar gates. So it's a bit.
Pull up and
Sorry, it's a bit.
you mean where this NAND gate is from?
Yeah, so like you need every single input to be like.
Right. So far we only talk about single input, right? So it's like just the same input and connected to pull up and pull down. So like we have a NAND gate here, right? Let's take a look at how we actually construct a NAND gate using CMOS logic. So if we look at the NAND gate, right? We talk about the truth table, right? So it's have two input A and B, and we have output, right? So when both A and B are 1, we get a low output, right? So this is a NAND function. So this is a NAND function that we have here, right? So now we think about how it can actually construct it using a pull-up network and pull-down network, right? And we talk about this as output, right? So if we think of behavior, let's look at the pull-down network, how we actually pull the signal to 0, right? It is pulled down to 0 when both of the inputs, both A and B are high, right? So in this case, we connect A and B together in serials, right? So when both A is on, both A and B is on, the entire pull-down network is on, that we can pull things down there.
But I guess that question is like, how do you make the
how do we design the pull-up and pull-down network?
Yeah.
You like say you have a Boolean function and how you actually figure out how you construct the pull-up and pull-down networks together? Or how do we design a NAND gate? It's okay. It's okay. Let's work through this together. And as what Justin asked is actually something we will actually talk about. If you have a Boolean equation, how you actually construct pull up and pull down network to implement that function. Right? Let's start on the simple gate. So here we have NAND gate, and we talk about when both inputs are on, and the entire pull down path is conducting, and then we can actually get a low signal, right? And if we look at the pull up network, we're using pull up network for the charging part. It's basically either A and B is on, either the PMOS transistor is on, we can actually, the pull up network is conducting, we can actually pull the signal up. So this is where basically for the inverted signal, it's like a parallel relationship because either path is conducting, it's actually the pull up network is conducting, right? So with this, you can actually think about how to actually express a Boolean function out of the CMOS transistor here. So if you look at the output here, right? If you look at the pull down path, it's basically as we put here, it's like both input need to be high so that the pull down network is conducting. When it's conducting, we talk about it's always inverting, right? So it's actually the inverted signal. So this is basically the NAND gate. Questions?
Like in reality, you have the pull-up network at the top where you have A and B in parallel and PMOS transistors. When you have A and B, it makes like a parallel circuit. So wouldn't it behave differently than just having only like A active or B active?
Yeah, that's a good question, right? So now you will say, if you think about when output is high, there are actually three scenarios, right? It could be actually both are on or one of them are on. That we'll talk a little bit later. That could actually lead to a different timing behavior, how fast it can actually charge the behavior. But yeah, there are like three parallel conditions that can actually lead to the same output, and that will have like timing implications there. We'll talk more later. Yeah. Any other thoughts, questions?
So when you send signals to both P and B, kind of goes together for both input of the signal, or
So like this will be like if you actually draw everything together, let me have a different color. So this is B. So we have two inputs. Both of the inputs are connected to both PMOS. So for each input, A or B, they are connected to both PMOS gates and the NMOS gates there. So it's the same input. It's actually connected to both the gates of both PMOS and NMOS. Any other question? Makes sense? Is everyone with me? Question?
You see like circles at the input all of them? So are you thinking B naught and A naught?
Oh, that's a good, let me clear this. That's a good question. So there are two types of circles connected here. That might be the source of confusion. First is this circle. Those circles means PMOS, right? So those only mean PMOS because it it's the opposite of NMOS. The other circle only means this is, you can almost ignore that as this is something connected. It's like connected to the input. And those are what we draw earlier connected to the output. It's just the way the diagram is drawing. But the first circle, the red circle I mentioned, those are important when those representing, those are PMOS.
The top are receiving not A, not B, and the bottom are receiving just A and B.
Oh, that's a good question, right? For the top in PMOS, are they receiving A or are they receiving not A? Nicholas? They're receiving A. Remember, they're the same signal. It's the circle here means just PMOS. The behavior will be different, but it's the same signal connected. So it's the same A. We're not adding another inverter behind that, right? It just means that this is a PMOS. That's a good question. Any other thoughts? Kind of makes sense. We see how this is going with building from a Boolean expression to actually construct gates. Joy?
So for the case where you have A and B are both 0, how does that give you a 1? I don't see that yet.
So let's say when both A is 0, B and 0, right? So when we have low voltage, which side of the network is conducting? PMOS or NMOS? When input is low. PMOS is conducting and both paths are conducting, right? Because both. So now both paths are conducting, which is charging the output. And when it's charged, this will be VDD, this will be a high, right? So that's why it is a 1. Yeah, good question. Are we on the same page? Kind of getting there. We'll go through a couple more exercise to actually get folks familiar with that. But yeah, so here it's really two input. We're talking about two input, right? And they're connected to both PMOS and NMOS, both pull up network and pull down network, right? So that we can get both strong 1 through pull up network and strong 0 through pull down network. Okay, so this is NAND gate. Let's take a look at another gate, right? So now we're doing a NOR gate now, right? So NOR gate, again, we have two input A and B, right? Now maybe let's look at the case when it is 1, right? So when both A and B are 0, we get a high output. So in this case, let me also draw this way. So it's the same signal A, the same signal B, right? So now if you look at my output, when both A and B is 0, like what Joy mentioned, when it is 0, the PMOS is conducted, right? Because PMOS is conducting when the input is 0. So we are charging the output, and so when it's 0, we get a 1 here. And if or another scenario, if let's say A is 1, but B is 0, so one of the pull down network is conducting, the pull up network is off, so my output get to 0 because I'm discharging, right? So this is a NOR gate, meaning if either of my input is 1, my pull down network is conducting, I start discharging, and whenever I discharge, I got to output 0, right? Does this make sense? The NOR, so this is a NOR connection, right? So it's inverted, and the NMOS network is on, either A or B is on, and so that's where we have A and B, and then things are inverted, right? So very handy way to actually look at the CMOS gates and think about what's the equation, what is the Boolean expression it's representing. It's actually always look, let's say the output is always look at the pull down network. It's just easier to look. So you have pull down network. We mentioned it's always inverting, right? Because when pull down network is on, you get an inverted signal, right? So it's inverting, and the pull down network, then you look at how the pull down network is constructed. In this case, A and B are in parallel. So it's a A or B relationship, right? Either of the condition is true, pull down network is on, and we are discharging. It's an inverted relationship, right? So this is a very handy way to look at a CMOS case and figure out what are the Boolean equations it represents.
So you have the circuits that are like in parallel, that means an OR representation, and then there's in series as an M.
Yes, yes. So we talk about, that's a good question. We talk about when, yeah, so when we talk about resistance, right? Resistor Ohm's law behavior, right? So when both are connected together, this is a serial relationship, and it basically means both. It's actually on when both, if we add a switch here using our switch model, both need to be on to actually have things connected. If things are in parallel, it means if either of the paths is on, things are conducting, right? So there's a serial and a parallel relationship. So here we see the pull down network is a parallel relationship, right? Either it's on, the pull down network is on, so it is a OR relationship, and like the pull up network is AND relationship, means both conditions need to be met. Yeah. Any other thoughts, things you have in mind? Okay. So we look at some simple gates, both PMOS, both NAND and NOR, to think about how we actually construct the how we actually take the, I guess, the gate representation and get the Boolean expression. Let's take a look at some of the more complex gates. Well, I'm trying to figure out, okay, how to erase this. Okay, let's look at the next one. Let's look at, let me do that here. So, give me 1 second. So it's a little bit hard to tell, but let me clear my annotation. My iPad stopped working. Oh. Okay, well, while I'm setting things up, let's see how. Let me try something. So it's a little bit hard to see, but try to see whether you can see what is a Boolean expression for this gate. And you can talk to your neighbors to understand what is this gate trying to do.
Yeah, because. You just have to like all the way to like. Supplementary doesn't just this. Oh, well, we were just getting some arbitrary. And we're just all the syllables around. This is, yeah. This gate triggers. So this only lets it pass. B and C are loved. We love like this. We can only do this back. He loves similar. That's not be done. Again, it's also not relevant. Well, maybe he knows something. That's not the one. Yeah, I like that one about this is also will discuss the this one you're not involved. Is just a idea. This one.
All right, well, let's wrap up the conversation in 10 seconds. All right, so we have an output. We have, this is a lot more complex. We have 4 input, A, B, C, and D. All right, now we want to know, what does this output represent? What is the Boolean expression for this gate? Any ideas? Anyone? Justin? A parentheses B plus C, close parentheses, plus D, and put a not. How did you get here? You look at the bottom, the pull down network. You can also read the top. Well, let's start with the bottom. So you do the pull down network. I guess we walk through the behavior. We talk about when things are in parallel, it is a OR relationship. When things in serial, this is AND relationship, right? So we do look at the pull down network. We do the A. So A is in serial with this box, right? So this box, so that's the parentheses. Inside the box, B and C are in parallel with each other. So we have an OR relationship, B and C. And then in addition to this path, there is an independent path that in parallel with the ABC path, the D path. So we have another OR relationship, right? And we mentioned it's always inverting. So we have this bar on top of the entire expression. Make sense? Any? What's up? Why? Oh, that's a good question. Is the pull down network the mirror of the pull up network or the dual of the pull up network? Yeah. Are we just duplicating? Like you will look at the pull up and network, they look identical? This like they have all the inputs, but they look slightly different, right? Right. Remember, you can actually, it would be a good exercise to use De Morgan's law to actually derive from the pull down network to the pull up. It's basically, you can actually apply De Morgan's law whenever you have AND relationship in the pull down network. It turned out to be an OR relation. Like you look at how D is connected to the ABC block, right? So in the pull down network, D is in parallel with the ABC block, right? And then we get to the pull up network, D is in serial with the pull down network. So, right, so it's not exact mirror, right? So it's a dual of the pull down network. Good question. And question? Oh, why there's a bar on the top here? So we just walk through this, the bottom part, this is expression, right? So this expression basically means if this condition is true, my pull down network is active, right? Right. For example, you look at D, if D is 1, D is on, my pull down network is active. And if my pull down network is active, I'm discharging, right? So that's why CMOS is inverting, right? So that's why it's always handy. Okay, there's a bar there because they inverted, and we're writing the condition when the pull down network is active. And when pull down network is active, we're discharging, right? So that's why there's a bar there. Any other question?
So when we're trying to get like the bullet expression, is it like we'll just look at like side of like either the PMOS and NMOS and rating it based off of either one? And if so, like which one is like the better option based on?
Right, that's a good question, right? We talk about PMOS and MOS are just dual of each other, right? So you can actually write both. This one is a little bit too much. Let's take a look at some simpler one. All right, so let's say we look at, okay. It's a little, I didn't know. Well, let's look at this, the NOR gate example we had earlier, right? So we mentioned if we look at the pull down network, we have this bar here, and we have either A or B is on, the pull down network is on, right? You can actually also write out from the pull up network. When pull up network is actually the inverted condition, right? So it's actually when either A bar is true or B bar is true, you have the pull up network, right? It basically this condition, right? And those two are equivalent from De Morgan's law that we mentioned earlier, right? Because they're just the dual of each other. Typically, it's easier to write from the pull down network. You don't need to take inverted input, right? Just write input as it is. So typically, I would recommend to write the pull down network. It's just easier, but you can actually walk through the behavior because there is the dual of each other. You should be able to arrive to the same conclusion. Yeah. Good question.
Assuming it's a correctly designed CMOS gate.
Assuming it's correctly designed and they are actually indeed the dual of each other. Yes.
They may see on your homework CMOS gates that may not.
Yes, exactly. Okay, good. Any other thoughts? It's getting there, a little bit overwhelming. It's getting okay.
So the next slide, is there a separate coordinate expression for the pull-up part, like the one that's up, or is it just?
Is there, say that question again?
For the expression right now, we have the TB and TG. That's for the one that's like the lower top, or is there a one upper?
You can actually write the expression similar to the exercise we did with Alberto earlier, but they should be just a dual of each other using it will actually be the same. Again, as Ben mentioned, if it's correctly designed, they should be just dual of each other. You can do both ways, yes. Okay, so that's our, I guess, a little bit more complex gate, and you can see actually how you, for a correctly constructed gate, how you can actually, from the transistor diagram, get to actually the gate representation. So far we talk about, we'll actually do more exercise in our homeworks. We'll get to play with a little bit more to see actually how we actually construct the CMOS gate. So far, we're mostly talking about the CMOS, how we actually construct complex gates from transistors. Next, we're actually going to get to the delay part, right? How we actually, now we see how we build those gates, right? From the basic building block. We talk about CMOS, PMOS, and NMOS transistor. We talk about inverters. We see we can also build more complex gates, right? Out of those basic building blocks. Next, we're going to talk about how we actually understand the delay, right? We always mention timing really important, especially for folks folks in the ASIC lab, you folks have already been seeing a lot of the delay reports, right? How we think about the delay, right? How we actually, what are the different factors that may actually impact the delay our circuit? And we'll start from inverter. Again, that's just the simplest gate that we can reason about, and then we can get to more complex gate later. So just very high level, we always mention frequency is really, really important when we think about transistor performance. In particular, and we look at actually how the past processor scaling, right? Having actually reliable growth out of frequency is always a very good way to actually improve end-to-end performance. Well, it's getting a lot harder these days to actually further increase the frequency, but it is always a very important metric that we need to think about in the hardware design. So specifically, when we actually think about delay optimization, right, what we really want to do is figure out the critical path, right, the longest path, the most important path in our design so that it doesn't actually limit the overall frequency of our system, right? So we'll make sure that we can speed up those important paths so that it doesn't limit the behavior. Of course, there are like a lot of different levels of optimization that you can apply. A lot of us are like very familiar with a high level architectural, even micro architectural, right? We talk about how we do pipelining, right? Pipeline is a great way of actually making the critical path shorter instead of having the entire stages of execution. The critical path is really one of the stages, right? So pipelining is always a very important one at the micro architectural level, right? At the lower level, there are always a lot of very important knobs that are also critical when we think about circuit performance, right? Of course, logic level, we talk about different gates, different building blocks that also have an impact on the overall timing behavior. We'll talk about the circuit level, in particular, the size of the transistor, which is actually very important knob. So far, it's like, oh, there's a transistor, right? But there's like physical behaviors of the length, of the width of the transistors, and that have implications on the overall delay of the circuit, right? And you will go lower level, like how you actually lay out your circuit, where things go where, even the wiring across them, all of them have very important implications when we think about timing. Right. So for this lecture, we'll actually think about very high level simple models, but we hope to actually offer intuitions on what are the implications when we think about different logic gates and also different behaviors or sizes of the gates and how that actually implicate the circuit behavior. A lot of those should be pretty familiar for someone who like at least took 105. Is basically we can actually think about a lot of transistor level behavior like RC circuit, and that's a very important and very useful knob for us to understand the timing behavior. We'll talk a little bit more about how we generalize from, I guess, a single inverter to a chain of inverter to a more representative of like more than complex circuit, and also to more complex gates, like some of the complex gates we just discussed earlier, how we think about the sizing of them, how we think about the delay implication of those transistors. And I mentioned earlier, we talk about how we generalize those to other gates. So to get things started, right, let's take a look at how we can use a simple RC resistor and capacitor model to think about inverter delay. All right, so when we think about inverters, we talk about the inverter is a gate, right? And we have input and output, right? When we think about circuit, it's typically, it drives something or something downstream actually being driven by my current stage, right? So let's just have something, we call it load, that's like, is represented as a capacitor representing the downstream circuit that we're driving, right? So for this very simple circuit, we have input, we have output, and it's driving some of the load represented as this load capacitance, right? What we're really interested for this discussion is how long does it take to actually, so the input, the changes in the input will be propagated to the changes of the output, right? What is the delay here for this propagation, right? So now we look at our transistor, like we talk about our transistor behavior, right? We mentioned it's the same input being connected to both PMOS. We're using our switch model. It's a switch and the resistors, and connect to the pull-down network is NMOS, right? Again, a switch and resistors. So here we are interested in how the output is transitioned from high to low, right? So we are interested in the delay, the timing of the, where this is delay is a propagation delay as a propagate gate from input to the output, right? And the output is going from high to low, right? So output is going from high to low, which means my input goes from low to high, right? So this is my input voltage. It goes over time because we're thinking about timing. So far, it's all just magic, right? Things just transition immediately. But now if we think about the timing behavior, we go from low to high for my input voltage. Now the question is, how long does it take for my output voltage, the propagation delay, transition from high to low, right? Because it takes time to transition, right? How long does it take? So you would really think hard on what is actually the circuit behavior look like, right? So when the input go from low to high, right? So now my input is high. When my input is high, which transistor is conducting? NMOS, the bottom, the pull down network, right? When my input is high, this switch is off, this switch is on, right? So when pull down network is conducting, this is basically a zoom in version of the circuit that we're looking at, right? My input is on, my pull down network is conducting, and what I'm doing is discharging behavior, right? I'm discharging whatever the charges accumulated in my output to the ground through the NMOS circuit, right? Does that make sense? Everyone with me so far? Good? Okay, great. So now we actually focus on, this is a circuit we are interested, this is an RC circuit that we are interested, and this is the output voltage, right? So you look at the output voltage. Before the transition, when input is low, my output voltage is high, right? Before input transition, my output voltage is high. And what we are doing once the NMOS circuit is connected is this discharging behavior, right? I start discharge from whatever the charge is accumulated to the ground, right? So it start at high. We'll figure out the transition in between, but let's say after long enough, what's the output voltage of what's the voltage of this output node? 0, it will be 0, right? After a while, it will be 0. So that's why it's an inverter, right? So when input is high, my output eventually will become 0. But it takes time to actually fully discharge, right? So now the question we'd like to understand here is, let's say also plot, like how long does it take for my output going from VDD to 0? Right, for that discussion, it's always useful to think about the current. This is the current actually going through this resistors, right? So now is my current going through this resistor. So this is basically a very simple RC circuit. We have C and we have R here, and we're doing a discharging here. Right. Another notation, in case you find it a little bit confusing, here we talk about the load capacitance, right? There's a load capacitance. We also have another capacitance here. We'll talk a little bit more about what that capacitance represents, but it is you can think of it as a parasitic capacitance that's more intrinsic to the gate. So we're actually driving both the two capacitance factor. One is from the load. One is from the gate itself, the transistor itself, as some non-ideal behavior. We'll talk more later. But here is the capacitance we're driving here. So now if we think about discharging, how fast does it discharge from the capacitors go through the pull-down network? Let's look at just some simple note of the behaviors. Let's say when over the time is 0, what is the current? Like now my input go from 0 to VDD all of a sudden, right? My NMOS is conducting. What is the current that is flowing through the resistor? Nicholas?
over R equivalent.
VDD over R equivalent. Yes. Why is that? Good job. Good. Why is that? V equal perfect. That's all you need for this class, right? So we talk about the voltage is a current flowing through it times the resistance of the path, right? So if you look at this path over the resistor here, right? The voltage here is output voltage, V out, right? At the time 0, V out is basically VDD, right? And then the resistance is R. So the current here right now is basically VDD over R. That's the current I'm discharging, right? So I'm start discharging now. And now eventually when VDD becomes 0, when this voltage, when the voltage over R become 0, again, V is I times R, right? When V is 0, current is also 0. There are no more charges, right? So you can think about once the circuit is conducting, all of a sudden I start discharge really, really quickly because the voltage difference over the resistor is pretty high. And then over time, my current decay gradually because the voltage difference, like over time, my voltage will V out will be going down. The voltage difference will be smaller. The current will be also smaller. Our discharge will be slowly. Does that make sense? It just overall is fundamentally just voltage is the current over the resistor. We'll not go too much about this. Eventually, you will actually see you can actually solve a differential equation to actually get how V out actually behave there using basically TVL. You can actually discharge there from the capacitors. You can actually get a more, I guess the equation for V out. But overall, if you think about the behavior, right, you start discharging really quickly, and then it's like current start decaying, like you have smaller current overall, and then until the circuit is stable. There's no more discharging behavior. Correspondingly, if you think about voltage, right, voltage is basically current over multiplied with the resistance, right? So the voltage will also decay over time until it's finally reach 0, right? So that's basically how the output node actually behave during the voltage of the output node actually decays during the process. Does this make sense? Very high level. When we actually go from 0 to VDD, all of a sudden we start discharging, and the discharging current at the very beginning is very strong because the voltage difference is high, and then over time it goes down gradually until it's fully discharged. Making sense? That's how the RC circuit behave. Again, for folks who are interested, you can actually just solve this differential equation. You can actually see how the current and the voltage behave. And eventually we'll look at the behaviors here, right? We'll look at the V output, right? We mentioned it's basically an exponential decay of the output of the original voltage. So it's basically, you think about V out, it's basically follow this pattern. No need to remember those equations. Again, just more importantly, it's really understand the principles, right? So it's basically the voltage. It takes time to decay here, right? So here, one thing that is actually very important is what we call the time constant, right? We mentioned this is a RC circuit, right? So the resistance in this circuit is basically the equivalent resistance of our NMOS. And then the capacitors in this circuit is basically, we'll talk a little bit more later, both the parasitic capacitors as part of the CMOS, part of the MOS transistors, and also the load capacitor, like things that I'm driving downstream, right? So those RC constant component are basically the time constant that is actually used when we think about how the voltage actually decays over time. And in particular, when we think about which is we'll look at, which is basically this constant here is the RC constant of the circuit, right? It dictates how fast it decays here. So in particular, we mentioned when we think about timing, it's propagation delay from high to low, right? How fast it takes to propagate the signal. Typically, we actually measure the time to propagate to propagate from VDD to a half of the VDD here. So basically measuring the time it takes. It's just like a typical way of thinking about propagation delay. After half of the voltage, things can be characterized or resolved here. And this is what people call the propagation delay. And in this particular case, it is the high to low. So it's basically how long it takes for voltage to get to half of the VDD here.
If I remember right, early on, we defined propagation delay as the time between when the input hits 50% and the output hits 50%. It looks like with this switch model, we're ignoring the first part.
We're getting there. So here, because input hitting 50% is immediate, right? It's at time zero. This is,
right.
yeah. So because we're ignoring, we'll talk a little bit more, input also doesn't happen ideally, right? But now we're isolated a little bit more. We're ignore the input part, our input happen immediately, but for output, this is a propagation delay, right? So propagation delay is basically when output is half of the VDD for this discussion. And then if you actually solve this, it's basically a ln 2 of the time constant. Ln 2 is roughly 0.7. So sometimes you will see the time constant being used, and the propagation delay is basically 0.7 of the ln 2 or 0.7 of the RC constant. And this is what we mean when we think about the propagation delay. Making sense? Overall, it's the exponential delay part. So far we talk about the high to low transition, focusing on discharging path, right? Let's take a look at the other path. It's again still the propagation delay, but it's actually low to high. Here we still assume input happened immediately, right? So we are not thinking about input behavior. So now input actually goes from high to low here, right? So now if you look at the behaviors here, my NMOS is off, my PMOS is conducting now, right? So now I'm actually doing a charging path, right? Because my pull up network is conducting. I'm pulling up the output to VDD. So I'm doing a charging path, right? That makes sense, right? So now we like to think about the propagation delay again. I mentioned this would be low to high. So now my output will be transitioning from low to high. What does the output voltage look like in this case? It's exponential again, right? It's going, so again, it's charging. So at the very beginning, it's 0, right? And eventually it will be charged to VDD. It will be fully charged, right? So now it's basically this charging path as we go from 0, right? The other way around, right? So this is basically how my PMOS will behave, right? So it's like charging gradually when we actually fully charged to VDD, right? So if you can write down, and for folks who are interested, you can also just solve the KVL equations, and then you get to the PMOS behavior. And similarly, it's also a factor of RC constant to actually fully charge from 0 to half of the VDD. So that's the propagation delay of the PMOS path.
What is similar, but there's no resistance for the.
Yeah, that's a good question, right? So far we just abstracted, right? We talk about there are 2 resistors. One is for NMOS, one is for PMOS, right? But what are those resistors? How to actually represent it? What are the values there, right? So we actually move on when we actually think about the resistors here, right? So we think about, again, let's use the NMOS path, right? So far, we're most talking about the timing behavior, right? The RC circuit, right? But the R part is basically the resistance of my NMOS path, right? So if we think about what are the resistance here, when we talk about this resistance, right? If you draw the NMOS again, right? So this is a gate, this is our source, this is our drain. We talk about like this can be viewed as a switch model, right? And the resistance is basically the equivalent resistance between my drain and source. Recall the current going through, right? Drain and source that we discussed before, right? So to get this resistance, we want to see voltage between drain and the source and the current before drain and the source. That's basically the resistance here, right? We did, in our discussion last week, we did a discussion on the different transistor level behaviors of the gate, of the current between drain and the source, and how that related with both the voltage between drain and the source and the voltage between gate and source. And in your homework, you will also run a SPICE simulation, so definitely take a look at it. That will be pretty useful. I recall we mentioned there are 3 regions of the current and voltage characteristics. Remember that? The first region is when the gate and the source is 0 or less than the threshold voltage. Nothing is conducting, right? My switch is not on, nothing is conducting, there's no current, right? Make sense? Right, so this is the first region, and we talk about then when the gate voltage is high enough and then my circuit is conducting, it will go through first more like a linear region. It's just like a resistors, and then it may actually saturate a little bit when you get to when the drain voltage is too high, right? So that's like the 3 region we mentioned between the current floating through the transistors and the voltage floating through the transistors. Make sense? All the memories are back, like the 3 very high level regions there, right? So once you have the IV characteristics, right? Resistance, like what Nicholas mentioned earlier, right? Just voltage divided by current, right? That's always a fundamental, like we're not talking about more complex physics, right? It just, resistance is just voltage between the 2 terminals and the current floating through that, right? So here, in the behavior we talk about, right, we are talking about how long it takes to actually charge, to in this case, discharge from VDD to half of the VDD, right? So now if you actually take a look at, you're basically, this is a path, right? You'll get from VDD to half of the VDD, and this is a current behavior, right? So for the voltage being applied here, this is a current behavior, right? Does this make sense? The IV characteristics. And for resistance, it's really just a slope. It's just a slope, right? With different points, you may have different resistance based on the voltage and the current, right? There are different ways you can characterize it. People run more complex simulations even to understand what is I guess the equivalent resistance. It's a variable resistor. It's not fixed, right? So it's fixed is easy, but it's a variable resistance. It dependent on how the voltage between the 2 terminals, and that will actually lead to different resistance. So it's a more variable resistor. There are like different ways you can approximate. We're basically looking at the equivalent resistance between the discharging phase. At a very high level, for a lot of discussion, you can maybe just think of it's like more like an averaged resistance between the 2 endpoints from VDD to half of VDD. But there are also more complex ways to model the current, the resistance in this phase. We'll not go into the details there, but you can think about how you use this IV characteristics to think about resistance.
Why is resistance you said for resistance is the over,
Right.
but isn't it's like
Oh, well, yeah, slope is so it's really just I guess not it's not the slope, it's just the xv over I, right? It just it's a linear curve here, not the slope per se. Yeah. So R is V over I, so I is V over R here. Right, so it's just divided. Voltage, for each point of the resistance, you get the voltage, you get the current, you calculate the resistance here. So that's a resistance here, and overall it is a variable. It's not fixed. There is a variable resistance when we think about the circuit behaviors. So here we talk about the RC behaviors of our charging and discharging paths for our inverters. And earlier, I guess Adam mentioned that so far we only talk about input actually goes very quickly from 0 to high, right? We ignore what we call the rise time, right? We talk about the propagation time, right? But it also takes time for a signal to rise from, let's say, from low to high, right? So this is a rise time, but we're talking about how long it takes for the input signal to rise from low to high, right? So now when we actually think about more non-ideal behaviors, now again, we're still talking about NMOS, this discharging path, right? So before we talk about, let me use blue to represent what we had before. Before we talk about the current between those, it's basically just go down exponentially, right? You have a very high current because it's fully conducting, and then eventually you get to 0. So that's what the current look like, right? So now we're saying even the voltage applied here is actually not directly VDD. It actually takes time to go, and this voltage is basically the gate voltage, right? So here is the gate voltage. We're talking about the gate voltage to our NMOS also takes time to go from 0 to VDD. So in this case, how does it impact, I guess, the current between drain and the source? So now it takes time for the gate voltage to rise. Maybe at the high level, when it also takes time for the gate voltage to rise, the question is that how that also impact the propagation delay. Let's take a look at the current first. So now the input voltage actually takes time to rise, right? It's not directly get to VDD. How does my current flowing through the NMOS transistor actually behave? It was like this before. Start with a high current and then go directly. Now, how does my current behave? Recall we talked about the current and voltage characteristics before. Before we only look at this part, right? But now we're talking about even for the gate voltage, we are actually rising it slowly, right? So how does that impact my overall current now? Brendan?
I'm sympathetic, rather than being significant to ITS, you'll probably see a rise and
Yeah, I guess Brendan is thinking whether it may actually go up first, it rise slowly, and then gradual fall. That's like what we saw earlier, right? So I guess what we saw earlier, this is basically the discharging, the decay part. Why it rises gradually?
the overall holding the overall IS.
So the input voltage here, so this gate voltage is increasing here. So when the gate voltage increase, how does it impact the transistor current? It allows more current to go through, right? We talk about here when we increase the gate voltage, right? We're basically jumping through the different curve because like now the channel is wider, it's more conducting, so it's actually also more current, right? So you can almost think of like while I was actually the voltage is shrinking, because we are actually applying different gate voltage here, it actually the current is slightly increasing because the channel is wider. You're still increasing, gradually accumulating the channel to get a higher, slightly gradually increasing the current, and then until the channel is fully conducting, then it's a decay part, right? So this is how factor in how that the gate voltage is also modulating the current that can flow through the transistors. So in this case, now it's actually the current, instead of just discharging immediately, the current actually need to accumulate a little bit while the channel is conducting, right? So now if we think about propagation delay, does it take longer for my output to discharge or take shorter? Where's the propagation delay now if we actually, the rise time is greater than 0? Does it take longer or shorter? It take longer because the current start with smaller, right? So when start discharging a little bit slower with slower current. So it actually take longer for my output voltage to fall, right? So instead it's immediately, this actually, when we factor in the more realistic behavior, it also takes longer for my current to discharge. Make sense? High level question?
So 2 questions. First one is, why do we assume that the voltage increases here? As a field friend of that friend?
Oh, well, here it's just it can also go in a more realistic. It's also go more like exponential. But just for simplified discussion, it rise and we just assume a linear input there for simplicity here. But the input basically rise gradually here. Right, and the right part is basically how the gate voltage would also impact the current, like we talk about the gate, drain, and the source, right? The gate voltage also modulate the channel, like we are gradually accumulating the channel start conducting, right? It's need to start first need to actually go above the threshold voltage, and then when the gate voltage is higher, you have wider channels, you can actually have a higher current flowing through the channel. So this is how the gate voltage is actually modulating the current here.
For with the rise and fall times, is it still exponential decrease by the test?
Well, we'll talk a little bit more, but like for example, the output of this node will become the input of the next circuit, right? So it's like how the output decays will actually become the input of the next stage circuit. Yes, it's always between drain and the source. It's always, so the increasing part, let me clear this. So the increasing part is what we discussed here, right? Because the gate is like gradually more open, it leads to like this increase part. And when we get to the decrease part, then it's basically this behavior here. Mm-hmm.
Do you explain the last one when you slowly increase down
so why this is much slower is so let me draw back so what we talked about before, the current is like this, right? It's best start from high and then start slowly discharging, right? So now the current actually, like what Joy mentioned, the current direction doesn't change. We're always discharging. So for the original one, it discharged very quickly as you have a bigger current, right? It's like discharged very, very quickly. You have the fixed charges accumulated. Now, because the current also needs to like gradually accumulate, so it's actually discharged slower, right? So if you think about the process, it's still this process, but the current dictates a rate of discharging. We have higher current discharge quickly, we have lower current discharge slowly. So that's why it takes longer to reach. It takes longer to reach half of the VDD here. So that's why it takes longer. Question? Yeah. So there are two parts. So if we go back to so you're saying, so current is actually, like accumulating, it's increasing. So the voltage is actually discharging quickly here. Or it's discharging. But what the discussion we had earlier is how is this discharging, I guess overall discharging process compared to the baseline when current start just high. So those are the two. Yes, so before it's like start high and discharge quickly. So now it takes time to accumulate. So that's why I discharge a little bit slowly. There was a question there. When IDS, when current is higher. So it's once the current is it's always discharging. So like it's a little bit hard to draw the rate, but it's always discharging. The voltage actually gradually going down. It's always like this. But even like what we are comparing is not like within this. It's like before the current was like very, very high. It's like because it's already high. This process is faster than this process there. That's what we are comparing against. Yeah. Okay, good question. So that's what we discussed on the behavior here, right? When we consider rise and fall time, I have a final exercise for everyone before everyone leaves the room. While you folks are still thinking about RC delay, right? Let's do one more exercise. We talk about RC delay. We talk about here NMOS, we're discharging, right? So now we're talking about how fast. Again, still the speed, how fast it discharges. What we do here is that we double the load capacitance. So here it's the same RC behavior. Instead of like a CL, my load capacitance double. I'm driving a bigger load now. So now the question is, how is my V out discharge process behave? Is that the green is a new one, right? So it's actually, in this case, faster, the same, or slower? Is a green, are we discharging faster or slower or the same when we actually increase a load capacity? Is that a clarification question or an answer? Answer? Okay, let's wait a little bit. Think a little bit, talk with your neighbors for 2 minutes and we'll get back to this. So now the only thing changed is the load capacitance. All right, so now we have higher load capacitance. Time constant is RC, yes.
So it takes longer.
What's that? The capacitor, the load capacitor? It is. Well, so we're using this load capacitor to represent the downstream circuit I'm driving, right? So it will be input capacitance of the next stage, right? So we're just like abstracted all the following circuit as a load capacitor. So I'm driving a load capacitor. That's a downstream circuit I'm driving. But now you can think about my downstream circuit get much bigger, a lot more complex. The question is my transistor get faster or slower?
Wait, are you doing it? It's just the initial slow. I think it's what?
Okay, we have a lot of heated discussions. Are we reaching conclusions? Ideas? Lawrence? Any idea? Is our circuit getting faster, slower, or stay the same? C? So remember our time constant, right? So the capacitance get bigger, it takes longer to discharge. So it's actually A little bit slower, that's correct. You can think about, you can use the equation, good job, everyone. You can use the equations to represent it, but at a very high level, you can also think about load is basically what I'm driving, right? I'm charging and discharging. Now I'm driving a much bigger thing. I'm much higher capacitance. I need to make more effort to actually drive it effectively, right? It takes longer to charge and discharge. That's why things get slower, right? We'll talk a little bit more. You can use RC constant. You can also think about principles, but you will have a larger circuit. It takes more effort to drive. I guess that's the end of the today's lecture. Just some very brief announcement. We don't have new lab this week, so use this lab to catch up. We'll be releasing the project specs this week, and looking forward to seeing all of you this Thursday. Good discussion.
Wait, there's gonna be people all the way out there. Are you ready for the hard one?